Assalamu alaikum. So last time uh, we started studying about the design, and I as described that there are three parts to signal processing. One is representation, the other one is implementation, and the third one is the design. And we have covered this, almost all of this except fast Fourier transform. We have covered this, the implementation part, and we started learning about design. And in design we said we will cover two aspects of design. One is design of infinite impulse response system, and the other one is design of finite impulse response system. So last time then we from design, once we say design, and I described that from this chapter's or this course perspective, design only means designing of a frequency selective filter. May they be low pass filter, band pass filter, or high pass filter. And I also mentioned that, as we know from our sampling chapter, that the highest digital frequency is pi. That also relates to fs over 2. Okay, so we covered that, and then we covered that ideal a filter like this is not possible, so we need to give some leverage for the frequency response to live in a range, and this range in the pass band is called pass band ripple, and it cannot just transition down to 0, so we need to give a transition band for the frequency response to go down to 0, and then it cannot remain 0, so you need to again give a little space for the frequency response to live in this space, and which is called the stop band ripples. So while we are designing a filter, and I know like you have done these labs, you need to specify delta 1, you need to specify delta 2, you need to specify omega pass, you need to specify omega c. Sometimes in terms of sampling frequency, as I mentioned. So sampling frequency, remembering that half of the sampling frequency corresponds to pi. So these are the design. Once you're designing a filter, you got to give these specification. And last time again I mentioned that this is called the pass band, this is called the transition band, and this is called the stop band. This is called the pass band ripple, and this is called the stop band ripple. So if you know this much, and you know the MATLAB filter design tool, you can really design nice filters. And then again, last time we spent little time learning about the comparison, that why should we design IIR or an FIR filter. And we said FIR, IIR, they are computationally effective because you need less smaller number of coefficients, but then you have also done a lab where you need to deal with coefficient quantization and nonlinear phase, whereas here you spend more in terms of computation, but you have comfort that you don't need to worry about stability, and it is also linear phase. So then we started learning about IIR, infinite impulse design of IIR filters, and as I told you, that nobody designed an IIR filter in digital domain. So they use all the work that people have done of designing IIR filter in continuous domain. Like people used to study this subject, analog filter design techniques. So you go back to those books and those chapters, and you borrow those methodologies of designing an analog IIR filter. So for the DSP people, they are smart, usually smart people. What they do is they have this specifications for a discrete time filter, so they convert it. And once they are converting, usually the simplest way of conversion is you take small omega is equal to capital omega into t. Okay, so you take small omega is equal to capital omega into t. So small omega frequency is converted into capital T, though you are not actually converting a discrete signal into a continuous only mathematically. So you assume any t. Okay, and then once you come back from here to here, you again go back from analog domain to discrete domain. So what you do is specs, you change the specs to continuous domain specs, means small omega is converted into capital omega with this capital T. And once you are here, you again sample and convert h of t into h of n, assuming some t. And here the t really loses its meaning. It is like I ask you that a dollar is 5 rupees, because I know I have to convert that rupee back to dollar. So whatever rate or whatever value of t you take is okay, because it is a two-way transaction. You are coming from here to here with a capital T, and you're going back to discrete domain using the same capital T. So t is in this technique is not important. So you can assume any value, even if you assume 1 or 1000 or 1 million, it's not going to make any difference in this whole process. So t can be assumed any value of your convenience. Okay, so you design and then you get to the discrete time design. So last time we covered that how you design a filter in Laplace domain or S domain. Okay, and so we said the analog filter design techniques these are the three famous analog filter design techniques: Butterworth, Chebyshev, elliptic design technique. Okay, Butterworth, I told you, must be a very genius person. He came up with the technique of designing an analog filter, converting an expression, which is a mathematical expression, into actually a circuit which has capacitors, resistors and inductors in it, basically passive filters. So I told you that he started with these specifications. So specifications are, as we know, the pass band and the transition band and the stop band. And then he used a function which is monotonically decreasing function of capital omega. So he came up with this expression, and this is basically the main trick of designing a filter, that he could come up with a mathematical expression for a frequency response which is in a closed form. This is important, it's a closed form expression. So you can see it's very precise, like in very nicely written mathematical expression, which says 1 over 1 plus j omega over j omega c raised to the power 2n. And this tells us that there are two unknowns. One is n, the other one is omega c. The filter design problem boils down to only finding value of capital N and omega c. And then we also spend time learning that how the j omega is converted into s. And this is how it was done. Like you have square means you multiply this with its conjugate. So this multiplied by its conjugate, replacing j omega with s, because once we put sigma is equal to 0, it becomes this. So this expression is converted into h of s, h of minus s. So instead of j omega, you have an s, because s is equal to sigma plus j omega. Once you put sigma is equal to 0, you get back to the original expression. Okay, so then I said you have to split it into two parts because you only want h of s, you don't want h of minus s. I also posted a question which I gave set for degree 30 computer engineering student, which was a simple to solve question from my perspective. There was no trick in it, because you know that you find out all the roots of the this expression in the denominator, and once you find out all the roots, you find out 2n roots, and they are symmetrically placed on the unit circle. So half of them you drop because they are on the right hand side. So you assign them to you assign those to h of minus s, and you assign these to h of minus s. So these are the location of the roots. You need to remember this formula, write it down on your cheat sheet, that these are the poles. So pk, these are the poles, 2n poles. Now if you know n and omega c, you can draw these. Only thing you need to know is n and omega c, and then you bring these on the left hand side and use this formula. Every pole s minus pole 1, s minus pole 2. So the number of poles on the left hand side, you write this expression, and this omega c raised to the power n, which is coming from this expression in the denominator. Okay, so this is the formula you need to remember. So you need to remember this formula, and you need to remember this formula. So you can solve almost any question in filter design, that if you know that these are the location of poles, obviously you have to find out n and omega c, and this is how you write. And then you combine, you can binomial expansion, so partial fractions, and you then you basically solve it. So we said, okay, if there are only two, then so these are the two. So these are the two poles, and this is the expression for h of s. So there is a question in the book that I started solving, which has given you a specifications that this point and this point. So I said there are 2 points are important because the equation has 2 unknowns. So if you can put this point in this expression, then you can put this point in the same expression. You basically generate 2 equations. If you have 2 equations, you solve them. So this is one equation. Similarly, there's another equation. You solve them, and you get value of n and omega c. Once you have n and omega c, you are done with the solution. And then you basically combine those, and you have an h of s. Now comes the actual question, because we have designed something which is in analog domain. But actually we want to design something in discrete domain, because we want to design a digital filter. So got to convert this into h of z. H of s has to be converted into h of z, and remember s is Laplace transform, which we use for analog systems. This is a transfer function of analog systems. Okay, hz is the transfer function for discrete systems. So how is it done? This is one technique which is called impulse invariance technique. Okay, we will learn 2 techniques today. We'll learn the other technique. So this is the impulse invariance technique. And what is the impulse invariance technique? Impulse invariance techniques primarily use a very simple trick. It says, let's take inverse Laplace transform, and once you have inverse Laplace transform, then you discretize it by replacing t by nt, and you get an h of n. And you got to lift the frequency response. We know, because once we sample, our response is 1 over t. So we got to scale it back to 1, and that's why you multiply it by t. Alright. So the process is very simple now. One process is that you have an h of s, and we understand that we have an h of s, and based on this h of s, we split it into factors, and then we basically take inverse Laplace transform, inverse Laplace transform, inverse Laplace transform. We get this expression, and this is kind of where we ended our chapter, that impulse invariance technique requires you to replace a t here. So wherever you see a t, you replace it with nt. This t is replaced by nt. This t is replaced by nt. So this instead of ut, it will become kind of un. This only telling that it's the right hand side sequence. You don't need to write n capital T. Even if you write u of n, it is okay. So you get this expression, and now you take the inverse. You take the z transform, and we know that this is like a raised to the power exponential p naught t. So you put it in alpha n u of n, because you know the Fourier transform of alpha f u of n is a z transform of alpha n u of n is 1 over 1 minus alpha z inverse. So once you take the z transform, you get this expression. And this tells us very simple. Again, you don't have to go through the whole process. All you know, and remember, you can keep t is equal to 1. So the pole comes, so right from where you have actually calculated the pole, so the pole comes on an exponential p naught z inverse. Because if it is left hand side, so exponential of negative is always less than 1. So this transformation guarantees that a pole which is on left hand side will map. So a left hand side S plane is mapped in z domain inside the unit circle. So a stable system here will result into a stable system here. So this is the transformation, and this is again an important formula, and this is the important formula. Now we understand that this is how the h of z is found. That every pole in S plane, you take exponential of that and exponential of that and exponential of that. It guarantees you that this value, because of the negative sigma value is negative, is going to be less than 1, less than 1, less than 1. So I expect you in the exam to at least able to write this, even if you cannot find A0, A1, A2, because that would require you to do some computation. But at least this is very simple. Like the question which I gave degree 13 exam, they should able to kind of solve it in 5 minutes if they know how to solve it. All they have to do is the location of the pole is given, and only they need to take exponential of that value, exponential of that value, exponential of that value, and they would have been done. The issue with, and this is where we start today, the issue is, and I'll tell you my personal story also on the topic which I'm going to cover. Interesting, a big turn in my life because of that kind of. So it is your sampling, okay? And the capital omega frequency spans from minus infinity to infinity. So once an analog filter is designed, you know, the frequency response goes from minus infinity to positive infinity. So you're not really worried about anything because the frequency span goes, and all you are worried about is the cutoff, that where it gets down, and then you don't worry about, because usually it is very, very small, almost, you know, just equal to 0 or. But once you sample, you know that you make a copy of the spectrum at every 2 pi, every 2 pi, every 2 pi. So these digital transformation may many copies contribute into altering or changing the frequency response of your the response which you actually started with, which is the analog filter frequency response. And sometimes, though you meet specifications of the filter in analog domain, but once you convert it into a digital filter and you plot h exponential j omega, and you find out it is no more meeting the specification, so you don't like this transformation. So this transformation has this basic flaw, and the flaw is that because of this, mathematically you are sampling, basically you are tricking it. You are start with digital, you go to analog, then it is analog, you sample, you go to digital. But this whole process is the process of sampling mathematically, and the process of sampling requires making copies of the spectrum multiple times, and it may alias. And once it alias, it may not, the ultimate digital filter may not meet the specifications, which we really don't like. So what do we do about it? Okay, so this must again be somebody genius who must be thinking about it, that it's a problem. So the problem he needs to solve is that there is this capital omega whose frequency axis runs from minus infinity to infinity. Okay, so the frequency axis runs from minus infinity to infinity, and he wants to design a digital filter where the frequency axis runs from minus pi to pi. Okay, one was sampling, where you just make copies, and it alias. The other obviously is that, is it possible to somehow compress it, like compress the whole frequency axis once you are converting it, and map this infinity to pi, and compress this frequency axis and map this minus pi, and rest of this, for example, if it look like this, it looks like that. Okay, so you have compressed it, and without changing the this axis, is the amplitude axis remain as. So you compress it from the both side, and you make this whole thing fix into pi and minus pi, so that if it is meeting the specification, if our filter is meeting these specifications, then the analog filter is meeting specifications, so we can guarantee that our digital filter will also meet these specifications, only it will be just compressed. Okay, but I don't care, as long as it is meeting my pass band, stop band, and transition band specifications. I really don't mind it changes its shape from this to this, because it is meeting my specification. And another reason is, now this omega p maps to capital omega p, this omega stop maps to capital. So first I have specification these, I convert them into specification these by expanding them in frequency, and then I come back to this. Because of this reason, I know that I have to change my specifications to capital omega, and then I need to change back. So I'm using the same transformation. So it will guarantee that if I'm meeting my specs here, I'll meet my specs here, because from here I transform my specs to analog, and then so this, some people must be thinking that how can this be possible, and somebody really smart could able to really figure out that yes, there is a function, you know, there is a mathematical function which maps infinity to pi. Just think about it, which function maps infinity to pi, and we have been seeing this function right from our FSC classes. It is tangent inverse function. It is like this. Remember, tangent inverse, you must have seen it in your FSC, that this is tangent inverse. So tangent inverse, actually it is not pi, it is pi by 2. So this is a little difference, that so this is tangent inverse is small omega. So tangent inverse of capital omega is equal to small omega. So this is a function, and we all know about this function, that tangent inverse of infinity is pi by 2, and tangent inverse of minus infinity is minus pi by 2. So we all know this function, okay? So, but the only thing which I don't want is for this tangent inverse infinity to give me pi by 2, I want it to give me pi. So what I do is I put a 2 here. That's it, So you put infinity, so it gives you pi by 2, 2 cancel, omega gets to pi, okay? And similarly, sir, we scale the x-axis of tangent function to map to pi. Yes, so we use tangent inverse function to map capital omega to small omega. So every value of capital omega is put into this expression and it is mapped to small omega. So this is the transformation. So this is a very simple mathematical transformation, which says small omega is equal to 2 tangent inverse omega, which will ensure that infinity is mapped to pi and minus infinity is mapped to minus pi. And so all the values from 0, from minus infinity to infinity are mapped from minus pi to pi. So basically this is how you basically do this transformation. But still I'm clueless. Okay, there is a function, but I have an h of s. How can I convert this into h of c? So still I'm clueless. Yes, good function. It converts my capital omega into small omega, and it fits the whole frequency response from minus infinity to infinity to minus pi and pi. Good. But I only care if somehow I can get a transformation, as we did in the previous case, where we went through a loop converting h of s to h of t to h of n to h of c. Okay, so we went through this loop, and this was the impulse invariant. So this loop was simple for me because I knew that I came to this by simply this transformation, which is a sampling. So once I converted my specs to analog specs, so I use this expression, which is expression for sampling. So I can go back to my h of z by using the same process, which is this process, the mathematics of sampling. This is not mathematics of sampling, okay? So because it's not mathematics of sampling, and now this again is very interesting, that how could actually he able to figure out this thing, and I'm really amazed. I don't know that how could he able to actually figure out that a transformation can basically make him. So does that mean that we are representing infinite frequency with pi in digital? Yes, we are basically representing infinity frequency by pi. But please remember that I don't care. This is all theoretical. Means this is not actually you are designing an analog filter using capacitor, inductor, resistors. You're just mathematically using the techniques. Okay, in that technique, the infinity, you want to bring that infinity back to pi, so that the specifications you have there, you meet those specifications, and still you have an analog filter. Okay, so now the interesting part again is that he could actually able to, from this mathematical expression, he could able to use this transformation. Okay, means if you replace every s in h of s with 1 minus z inverse over 1 plus z inverse, h of s gets converted into h of z. Okay, good. But from where this expression has come, like what magic have I played? Right, I have this transformation. how can I say this is actually this transformation? And this is interesting. Okay, how can I say this is actually this transformation is the interesting part, that I need to prove this, that these two transformations are actually the same, which is so I take this, I can convert this into capital omega is equal to tangent omega over 2. Okay, they are both the same. Okay, so we now let us see that the person who could actually give us this very interesting transformation basically are the same. So let's start with this one. Okay, so we have two things. One is this, and somehow somebody figured out that this is actually this simple transformation which will convert an expression in S into an expression in Z. And I'll tell you its significance. It has a lot of significance in converting any analog system, because every analog system has a transfer function. So you can actually convert electronic boards, electronic designs, electronic systems into a computer program by using this transformation. Okay, you can just throw away all the electronics if you know the transfer function. Convert the transfer function into h of z. H of z gets converted into a difference equation. Implement the difference equation through a computer program. So almost any analog system can be converted into a computer program. So it is the significance of this expression, that any analog system you find today which can be represented, and usually analog systems are the systems which are designed having a transfer function. So it can be converted into a computer program which you can write in 5 minutes, because you know how to implement an IAR difference equation using any of the techniques we have learned. So this has a lot of significance. So let's see that how these two are related. S means sigma plus j omega, and Z means R exponential j omega. 1 plus R exponential j omega. Okay, and we also know, and there is another proof of this also, that for continuous domain, once we go from S to omega, we put sigma is equal to 0, and for Z we put R is equal to 1. Okay, and we can mathematically also prove this, and this transformation ensures that, but we know this. So it is j omega is equal to 1 minus exponential minus j omega, 1 plus R exponential, sorry, R is no more there, minus j omega. Okay, so this is fine. Now what I can do is I can split this one into two. This is a technique which is very common in signal processing, that you have, if you have this expression, you can simplify it by splitting this one into two exponentials, minus j omega over 2 and plus j omega over 2, and splitting the negative into 2, minus j omega over 2 into exponential minus j omega over 2. So minus j omega will make a minus j omega over 2 will make a j omega, and this, remember this, once you add you will get a 1. And similarly here you have exponential minus j omega over 2, exponential j omega over 2, and similarly plus exponential minus j omega over 2. So this is a technique which is used a lot in signal processing. And now as you can see, we can take this as common. So this has common, this has common, so cancel out, cancel out, cancel out. Because you take common, you cancel out these, and this is j omega. So now you are left with exponential j omega over 2 minus exponential minus j omega over 2 divided by exponential j omega over 2 plus exponential minus j omega over 2. So this and this we know it is 2j sine of omega over 2, and this is 2j, 2 only cosine of omega. Euler identity, we know exponential theta plus exponential minus theta is 2 cosine of theta. So 2 cancels with 2, this j cancels with this j, and so capital omega is equal to tangent omega over 2. So So we got to this. And if we take the inverse, it is omega is equal to 2 tangent inverse capital omega. So hence proved that hence proof that this transformation is actually this. And what you have to do is you got to go, he must have gone in reverse direction. He said, okay, I have this, so this means this, this means this, this means this, this means this, this means this. Oh, bingo, 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 bingo. I got a transformation. Wow. So he must have gone in the reverse direction. And I don't know how he could actually be able to figure out this thing. Is not, though it's very simple to prove, it's not very trivial that somebody's mind would work in this way to find out a transformation, which is so simple to apply. So simple to apply. Why it is so simple to apply? For example, you have a transfer function, you have designed a transfer function. So we have, like, here is an example. You have an h of s, which is equal to 1 over s plus 2. Okay, it has a single pole at minus 2, which is a stable system, and this you can implement using because it's a first order, so either an RC circuit. This is basically an RC circuit, a resistor and capacitor circuit. You can implement this because it basically is a first order differential equation. If you convert this S into dy over dt, it's a first order differential equation. So you can implement it using a capacitor, and so this is the relationship. You have Vi and Vout. So this circuit, basically its transfer function will be something like this. And you can, in design techniques, you can actually figure out the value of capacitor and this inductor, or capacitor and the resistor for this particular transfer function. Okay, so you can figure this out. I'm not getting into that. I'm not even interested. I'm just telling you that this is what it is. And now you can convert it into a computer program. That's what I'm saying. Okay, this simple circuit, instead of actually putting these things on the breadboard, feeding in Vi, and then getting V out, you say, wow, why should not I convert it into a simple single order difference equation and write a program? Obviously, I need to digitize input and then I need to convert the output back to analog, which I really don't mind, but I can actually throw away this. So I say throw away this. Let me write a computer program by using this transformation. Okay, so this transformation says replace S by 1 minus Z inverse over 1 plus Z inverse. So you say H of Z is equal to 1 over 1 minus Z inverse over 1 plus Z inverse plus 2. That's it. So you are done. Okay. Obviously, you should simplify it. Don't leave it that ugly. And knowing all the things which we know, so taking LCM, bringing it up, then 1 minus Z inverse plus 2 plus 2Z inverse. I'm just simplifying it so that it looks neat. So 2 plus 1 is 3. 2Z inverse minus Z inverse is minus Z inverse. Okay. So usually I like 1 here. So you can, if you want to divide it by 3, but you can write a difference equation. Okay, it is 3y, but let me just do this. So 3y of n is equal to y of n minus 1 plus x of n plus x of n minus 1, and you divide it by 3, it becomes 1 over 3, 1 over 3, 1 over 3. Actually here you can divide and multiply. 3, 3, this goes away, and this becomes 1 over 3. Another thing what you see is that this 1 over 3 is less than 1. So a pole in left hand side S plane guarantees a pole which is less than 1. This is because for the transformation to be a valid transformation, a stable system must result into a stable system. So this is the computer program which you write. And anybody now we after in the stage of the course, and even if you have not taken this course, you can actually implement an equation like this. Okay, so this is good. This the second thing, which is also very trivial to prove, is once S is 1 minus Z inverse over 1 plus Z inverse. Okay, so Z, if you do some mathematical manipulation, you will figure out this is. Okay, so now if you convert Z into R exponential j omega, this is 1 plus S is omega plus j omega, or capital omega, and 1 minus sigma minus j omega. I know this expression. Okay, so so this is the real part, and so if I take the magnitude square, R exponential j omega magnitude square, okay, so it is 1 plus sigma square plus omega naught ka square and 1 minus sigma square plus omega naught ka square. So this is the magnitude square. And as you can see, if you put sigma is equal to 0, if you put sigma is equal to 0 to find out what this j omega x is, would result into, because this is sigma and j omega. So you get 1 plus omega naught square and 1 minus omega naught, so 1 plus omega naught square cancel out to 1. So R is 1. So it tells us that this omega axis maps to the unit circle in Z domain. Okay, and it also tells you that if omega is negative, okay, means it is left hand side as plane. So so then the denominator value will be greater than the numerator value. Mean for negative value of omega, the Z will always be less than 1. Means that a stable system in S will result in a stable system in Z domain. So this is a really big consequence of designing a digital filter, such a simple transformation, that all you have to do is that design an HFS, go through the same process as Butterworth filter says, find out N, find out omega C, go find out that, and then once you have an HFS, convert it into H of Z. So you are saying it is 3 plus Z inverse. So yeah, maybe let me see, where is that? Okay, 3 2 plus 1 is 3, yeah, plus, so it is plus, yeah, no problem, right? So he's right, it is plus, so this will be minus, it does not matter, so it is plus, is fine. Okay, so now but remember that once we are asked, actually we are given a question, and let's go and solve a complete question so that we understand that how this whole thing works. So usually a filter design problem, a digital filter design problem will be given like this, that you are given specification as you put in MATLAB as well, and you have done this, in MATLAB you got to specify, so you got to specify this, if this is 1, so you need to specify delta of 1. In MATLAB design toolbox, you need to give delta of 1, you need to give delta of 2, you need to give omega of p, and you need to give omega of s, where highest frequency is pi. So this is what we expect you to provide these specifications if you want us to design a filter, and this is an analog filter, h exponential j omega. These are the specs. So the question which we solved earlier, this value was 0.89125, question from the book, and this value was 0.17783. Okay, omega p was 0.2 pi, and omega stop was 0.3 pi, right? So this is a question, and you are now need to design, and design means you need to give an h of z. You need to give an h of z for these specifications, something that fits into, so it is, if it is Butterworth's, monotonically decreasing function passing from this point, and then going down like this. Okay, but first you need to convert these specifications into capital omega specification. The first part is, and if you remember, I told you that once you are converting, you use the same transformation. So we have a transformation. You need to same transformation from converting this into capital omega, because the capital omega frequency, it varies from 0 to infinity. Okay, and you don't mind, so you say, okay, I know that capital omega is equal to tangent omega over 2. So you put 0.2 pi here, divided by 2, take the tangent, and you will get a value of omega. So you put it here. This is your omega p. So capital omega p, which is equal to tangent 0.2 pi over 2. And this is your omega of s. Same, first you need to put tangent of 0.3 pi divided by 2. So use your calculator, find out these values. So I don't mind, because I know once I go back, it will again map to something like this. So I'm not really too concerned about this. This is not going to change, and similarly this is not going. So 1 is not going to change, 0.89125 is not going to change, 0.17783 is not going to change. Only this, you are expanding somehow the axis, going from small omega to capital omega. Now the function would maybe look like this. Why should I care? I don't mind, okay, because I know that I'm going to go back to like this. Okay. So now we go back to the whole process, and remember what was that in the Butterworth? It was HC j omega square is equal to 1 over 1 plus omega c raised to the power 2n. So first we put this point. So there are 2 points. First we put this point, value of omega, we put this value, and sc j omega, we put this value. So this is 1 point. Then we put this point, make another equation. So you have 2 equations, 2 unknown, and using the 2 equations, 2 unknown, I'll show you these values as well. So you figure out n has to be, and you get a value 5.3, but then you need n to be a whole number, and omega c is 0.766. Okay, knowing this, this is omega c. These are the 2 unknowns. Now you are done with the design part, and you know there are going to be 12 poles. So you have this circle of radius omega c, 6 poles here, 6 poles here. Okay, so if you have 180 divided by 6, 30 degrees. So at 30 degrees each. So first is here 15 degrees, 15 degrees. It is around pi by 2x, if you remember, I told you. And now 30 degrees, 15 plus 30 plus 30 plus 30 plus 30 plus 30. These are the 6 poles. And so this you can say P0 is complex conjugate P1, P2, P3, P4, P5. So these are the 6 filter, and they will always be in complex conjugate pair. Complex conjugate pair. Okay, always. So from this you find out the expressions. A lot of calculations which I myself hates to do, but sometimes this is MATLAB is doing for you, so you don't mind. But if you have to do this in exam, then it's really very bothering, which I try not to give you questions that where you have to spend all day in just making these calculations, and because it's omega c raised to the power 6, and this is your expression s minus p0, s minus p1, s minus p2, s minus p5. So you get an expression of And if you combine these, combine 2, combine 2, combine 2, they will become, remember, second order section, second order section, second order. That's what we prefer, that we prefer second order, 3 second order sections. So interestingly, you will find out that your h of s will be something like this, 0.20238, now writing exact expression, s square plus 0.3996s plus 0.5871. This is the first, and then there's going to be a second order, second order, okay? So once you combine the 3 complex conjugate pairs together, you get this as an expression. And now the transformation is very simple. All you have to do is replace s by 1 minus the inverse, 1 plus the inverse. Okay, and again, I don't want you to do this actually yourself because it'll take you forever by replacing s, but you know, MATLAB can help you to do that. And if you do that, your h of z is going to be now an expression in z, and where the second order section will be, this section will be converted into something. I'm just writing this value so that you know, you get an expression in z inverse. So the order will also not change. The second order, then there is going to be another second order and another second order, and there's something here as well. But through this, now you could actually able to design a filter where you don't have to worry about that the outcome, the final filter will be different. It may not meet the specification. That basically issue is resolved. This nonlinear transformation would ensure that you meet these specifications, which is really something very significant and big from our perspective. So this brings me to, just let me show you some of this on my slides and why I mention that it has some significance in my life as well. Okay, so let me just show you that here. Okay, so this is the impulse invariance. Okay, and if you remember, in impulse invariance, the transformation was simple, that s of k gets onto an exponential. Okay, so a transfer function would change. So this is the same example done for the impulse invariance. You have an h of s, and h of s is converted into h of z by that transformation, which we have seen. So you have 2 equations. So remember that 2 equations, 2 unknown, these are the specs. So you have this number and this number and this and this, and you put these 2 points in an equation like this. So you put this value here for 0.2 pi and this value here for 0.3 pi, solve it, you get an n, and this is, we are doing impulse invariance. And so you have these 12 poles, give 6 of them, so second order section, second order section, second order section, and you get to a function using impulse invariance. And impulse invariance means that you take inverse Laplace transform, you get this expression, then you take t to nt, you get this expression, then you take its z transform, but you can directly come down to this that we have already discussed. So you get an h of z, and this is an h of z, and you have to make fractions and an expansion, and then you combine the conjugate pairs together to get to this. And the problem with this is what I highlighted, that this may meet specs, but this may not meet specifications, you know. So you are designing, this is a good example, like this is a filter you design using Chebyshev type 2 technique, order 10. And but once you convert this into a digital filter, this no more meets specification. So you say, whoa, I don't want this because it is not meeting my specification. So I need some other technique. Okay, so this is not meeting specifications. So that is the reason we came up with this. And you see this 2 by t, and so I don't care about t, as I mentioned earlier. So you can just keep t is equal to 2 cancels out. So make it simple. You need not to make it complicated. Okay, and so capital T can be thought of as 2. So make the simple expression. But this is the curve which takes infinity and maps to infinity is mapped to pi. So that this entire left hand side as plane is mapped inside the unit circle. So this is the transformation. We have seen the transformation, and we have also seen that sigma naught 0 is mapped to z is equal to 1. Okay, so we have seen that this is the bilinear transformation. So this is the transformation. We need to remember this transformation. Z is equal to 1 plus s over 1 minus s. And we have done this as well. And we know that this is the transformation. Capital omega is equal to small omega over t. And we have gone through this whole process of proving that yes, this is how the case is. So basically it will bring infinity through this transformation to pi. So infinity is mapped to pi. Infinity here is mapped to pi. So you see this and this. So it may change shape, but I don't care about the shape. All I care is that it is meeting my specifications. You know, this is the first job I got at Georgia Tech, and I was there, was hired as a research associate in an aerospace lab where they were controlling the surge and rotating stall of a jet engine. And there were like about six, 7 PhDs who were working on this US Air Force project of bringing a jet engine never to stall. Even if you stop that engine or you put it in this, try to make sure that through a controller it will never let this engine to stall. And how was it done? They had several bleeding valves in this engine, and they would just change the pressures if they find out their sensors, like pressure sensors, and they figure out that the engine or the compressor is getting into stall, and they will bleed some of the airs from different parts of the compressor and bring the engine back to operational, into working. So I was hired on this project, and there were these crazy aerospace engineers and who would design a transfer function H of S. Okay, so they will give me a transfer function, and my job was to actually use this transfer function, convert it into H of Z, convert it into a difference equation, and then simply implement. So my input X of n was the pressure sensor in some part of the engine, and my output was the actuating signal I give to a bleeding valve to bleed some of the air. Okay, so they have like the testing different pressure sensors in different locations of the compressors and finding out which one is the best. And for every pressure sensor, they could bleed a valve, and for every valve there was a difference equation like this. So I had such a simple job that I would take H of S, use bilinear transformation, convert it into H of Z, and put a difference equation, and I'll work 3 hours in this lab and make a lot of money for them, because they had no clue how to convert an H of S into a computer program. So I was doing that for them. This is my first experience of actually writing C program, and here all these tables, I'm seeing the values of the pressure, and they would actually run the engine on weekends, and they will do the experimentation and see that how this whole thing works. So this my first job relates to this very little knowledge of signal processing of bilinear transformation, and I worked in this lab for more than 1 year. So we have seen that once small omega p and small omega s are given, they are to be converted into capital omega p and capital omega s. Okay, and then primarily once you have converted them, and only then you apply the transformation. So first is you are given the specs, given value of this and given value of this. So you convert these small omega into Hj omega specs, and the frequencies will change. Now this is the frequency and this is the frequencies. Okay, I've shown you earlier that. So you have the specs, small omega p, small omega s, and this is pi. You convert them into capital omega p into capital omega s. Okay, so these are the specs conversion, and so you do that using the same mathematical formula, and then you make two equations. First put this value of omega here, okay, which is this value, and Hcj omega here, which is this value, and similarly value of omega and value of this. So two equations, these are the two equations, and solve them. So you have two equations and two unknowns. Remember that once you have these specs, so you put this point and you put this point, and then solve them simultaneously, and solving them simultaneously will give you n. So this is, once you solve it, quite complicated substitutions which I'm not getting into, but you have these slides, so you can, if somebody is interested, you can spend an hour or so in actually solving these and finding out n omega c, and then finding out all the 12 poles. Put half of them in left hand side, so 6. So you find out that this is a transfer function, first second order section, second and third, and then replacing s with 1 over 1 minus z inverse over 1 plus z inverse will convert them into these, and obviously yes here. So you have an h of z, you have an h of z, so you're done with this. So the good thing about binomial transformation is that what you design in h of s j omega domain will meet specification. And remember, I told you this, that this is an RC circuit. Okay, there is a resistor and a capacitor, and this transfer function is alpha over s plus alpha, and alpha value is 1 over RC. So you can, if you are given an expression or a circuit, you can convert it into a transfer function. A transfer function means now you put s, replace s with 1 minus z inverse over 1 plus z inverse, and you get a difference equation. You implement a difference equation and you are done with this. Similarly, any electronics, you will find out that people who design electronics would always convert whatever they have into a transfer function. So a transfer function, even this is an active circuit, it's an op-amp, but it also has a transfer function, and you have a transfer function. Whenever you see a transfer function, you should be very happy, because a transfer function simply means a difference equation, and you implement the difference equation. So for example, this is an RLC circuit. So you see, this is an RLC circuit. This is a resistor, an inductor, a resistor, an inductor, and a capacitor. Okay, and you might have done this in your electronics, your first course in electronics, and RLC circuit, and this is the transfer function. So you can precisely implement this, okay, knowing what we know now, a second order difference equation. And you know how easy to implement a second order difference equation. So you apply that. So whatever input you give here, if you discretize and give that to a second order difference equation, it will give you the same output, almost same output, what you're expecting here. So the circuits can be converted into a computer program by using binomial, by using this distribution. Okay, it's not important. So this is the part where we are designing analog, from analog to digital IAR filters, and now we need to shift to designing FIR filters. So for that, let us take a break, and we'll come back in 5 minutes, and then we start learning about the second part of the course, which is, or the second part of the chapter, which is how to design FIR filters. And we will learn that FIR filters, because these filters don't exist in analog domain, so these filters are designed in discrete domain. So let's wait, just relax for 5 minutes and come back, and we start this part of the course now.